Today we're going to discuss about cryogenic safety, okay, from the safety masters. So we'll be covering the basics of cryogenic liquids. That's going to be quite a lot of them because we need to understand the basics first, and then we'll look into the applications of cryogenic liquids, the focus on the cryogenic liquids, and then we look at the concentration, mixtures, and explosion limits of this cryogenic liquids if it's flammable, and other hazards of cryogenic liquids. Then we look into safe storage and handling procedures related to cryogenic liquids, and we look at the hazards and risk analysis. We'll take a case study and we'll study this hazards and risk analysis. And then we'll look into the impacts of cryogenic liquids and what is the future of it and all that. And then we'll have a question hour. I'll keep the question hour almost 30 minutes. The reason is more questions you have, you can learn better about cryogenic liquid safety, as well as you can clear your doubts. Okay, so with that brief introduction, let me move on to the basics. So cryogenic, it's a Greek word. Okay, cryo means very cold. Okay, genic is the science. So this word was coined by Camerling Owens in 1894. Camerling Owens is the inventor of the helium liquefier. Okay, and he's a Nobel laureate. Okay, and there are many cryogenic histories. It goes back even beyond 1894. Okay, you had Dewar, you had Linde, you have many people in the history behind cryogenic. It's quite a topic to be covered, but I'm not going to go to the history of it, but I'm just wanting to introduce you to the word cryogenic, which is a Greek word, and it was coined by Camerling Owens in 1894. It means science and art of producing cold. Okay, so that's the meaning of the word. And in scientific terms or scientific community, cryogenic is defined as a science and engineering phenomena occurring below 123 Kelvin, that is minus 150 degrees centigrade, at normal boiling, at normal atmospheric pressure. Okay, a normal boiling point at 1 atmospheric pressure. So that is the criteria on which the cryogenic fluids have been defined. And then you have we look into the what are the constituents of an atmospheric air. Okay, in here you have nitrogen, oxygen, argon, neon, xenon, and krypton. These are the inert gases, and the oxidizer is oxygen. And then you have these noble gases like neon, xenon, and krypton. All this is coming from the atmospheric air. Okay, so we'll focus on the air separation and liquefaction of these gases, and then we look into liquefied natural gas. And some of you who are from the petroleum industry know about liquefied natural gas, which I'm not going to elaborate. And then we will look into liquid hydrogen and helium, how they are liquefied. And dry ice is, though it's doesn't come under the preview of cryogenic. If you look at the definition below 120 Kelvin, dry ice in fact is much liquid carbon dioxide boils at much higher temperature, but still we can consider it under preview of cryogenic because it's quite behaves the same way as any other cryogenic liquids in terms of safety is concerned. Okay, so with that basic, look into this basic of each of these components. So look at the properties of this cryogenic liquids. So you have the important cryogenic liquids. Even though I've taken propane and ethane, which is a higher boiling point, but they are stored in a liquefied form. That's the reason why we consider it as a cryogenic liquid. And then you have the xenon, krypton, which are the noble gases. Okay, so their boiling point is 165 Kelvin, and krypton is 119 Kelvin. And then you have methane, which is still higher, but we consider methane as part of the cryogeny because they are stored at low temperature. Then you have argon, oxygen, and nitrogen, which the industrial gas deals with the boiling temperatures around 87 Kelvin, 90 Kelvin in case of oxygen, and 77 Kelvin in case of nitrogen. Then neon, which is again a noble gas, the boiling temperature 27, and then as you go lower, hydrogen is 20 Kelvin. So in hydrogen you have ortho and para. So ortho para exists in the gas form, but as you liquefy, it turns into para. Okay, so that's specialty about the molecular structure of hydrogen at low temperature. And then helium, which boils at 4.2 Kelvin, almost close to absolute zero. It's like minus 270 degrees centigrade. Okay, very close to that. So there's one more thing about this table you need to look at is the volume of expansion. For example, if we take nitrogen, one volume of gas at 1 bar will expand to 720 times. Okay, so that's one of the hazards. Okay, similarly, if you look at neon, it is 1488. And also you need to look at the density, okay, of gas, because if some of the gases may be heavier than air. If you look at, like, for example, nitrogen, it's heavier than air. Okay, and if you look at hydrogen, it is lighter than air, 0.081. Okay, if you look at helium, it's lighter than air. So you need to understand its properties, and based on this, those hazards can be determined. Okay, similarly, densities of these boiling points. Okay, so now this cryogenic liquids can be also classified as inert gases, flammable gases, or oxidizer. The inert gases are nitrogen, helium, neon, argon, and krypton. The flammable gases are hydrogen, methane, and liquefied natural gas. And the oxidizer is liquid oxygen. Okay, so they are classified based on this classification, because the safety of this gases, if inert gas, you can have a similar safety procedures for all this. Flammable gas has similar safety procedures. An oxidizer, again, is a set of procedures for the oxidizer. Now, these are some pictures of the cryogenic liquid. Now, the one you find here on the top left is liquid helium. Okay, droplets. Even just below this one is also liquid helium. And this is the one which is burning is the natural gas, okay, the petroleum gas. And the one which you don't see at all any flame, it's the hydrogen flame. Hydrogen flame, you cannot see it in naked eye. Okay, and then the blue color you see here is the blue color you see here. Just a minute. The blue color you see here is the liquid oxygen. Liquid oxygen is bluish in color. And this, we see this gentleman pouring some liquid, which is a lot of vapors. This is liquid nitrogen. Okay, so handling is the issue. He doesn't have wearing gloves on it, but over that, many of the laboratories or many of the industries, they do use it. He's using a flask to transfer liquid nitrogen. The vapors are formed, and vapor displaces oxygen, so there is an oxygen deficiency hazards when handling nitrogen, which I'll come to it later. You see on flask here where someone is pouring liquid onto another bucket. So this is liquid hydrogen, and the one in the center which you see is a solid carbon dioxide and liquid carbon dioxide. So just to give an idea how this liquids looks like, and they are a very low temperature, very low temperature. Okay, so there are hazards of frostbite, hypothermia, which come to it later. Okay, now let us look at the various production methods. So one of the standard production methods of cryogenic liquid is air separation plant, where you take air inside the plant using a compressor, and then you separate the air into nitrogen, oxygen, argon, and other noble gases, depending on using the distillation column and depending on the purities you require. Okay, so air separation plant is one method of producing cryogenic liquids, but that's not the only method. There are several other methods of producing cryogenic liquids, such as Joule-Thomson cooler, JT coolers. Okay, and then you have Gifford-McMahon cryocoolers called GM cryocoolers. And then you have Stirling cryogenerators, which can produce liquid nitrogen. You can produce it as a laboratory scale liquid nitrogen. Okay. And then you have there are two liquefiers. Okay, they are basically liquefier cycles, which is generally used in many cryogenic applications. One is Claude cycle for liquid hydrogen production, and Linde-Hampson cycle for liquid hydrogen production. Now, the one previously which you saw is for producing the cryogenic liquids like liquid nitrogen, liquid oxygen, liquid argon, and noble gases. And J2 coolers are for producing liquefying helium. And Gifford-McMahon's cryocoolers is also for producing liquid helium. Stirling cryogenerators for producing liquid nitrogen. JT coolers can be also produced for producing liquid helium and liquid hydrogen. Now, for producing liquid hydrogen, you can also use two different cycles. One is called the Claude cycle, the other is called Linde-Hampson cycle. Are you able to hear clearly? Okay. Now,
yes.
Yes. Now, Claude cycle is it's a patented by Air Liquide, and Linde-Hampson cycle. Linde is Linde and Claude. Claude is the inventors or the founder for Air Liquide, and Linde is the founder for the Linde Group. Okay, Hampson is nothing but our British oxygen company, which BOC. So Hampson patent was taken by the BOC, and BOC is formed out of Hampson. Now BOC and Linde have joined together, so you have Linde-Hampson. Okay, so both the patents are together with one company, that's Linde Group. Okay, so Linde-Hampson cycle, you don't have an expander. Okay, you don't have an expander in Linde-Hampson cycle, but in Claude cycle you have an expander. So that's the only difference. Remaining, there is an heat exchanger, but the basic difference is the expander. And then you have other methods of producing. One is called the recuperative cycle, and another is called regenerative cycle. I'm just giving you some ideas. Okay, Joule-Thomson is one method of producing. It's all liquefiers. Okay, and I've already given you introduction of Joule-Thomson. Then you have a Breton cycle. Okay, which is again a cycle which can be used for which is a recuperative cycle. Okay, so you have a heat exchanger where you have the coal gas produced, and then the returning vapor will also cool the incoming gas. It's a cyclic process. And the regenerative cycle, one is on charge, another is on recharge. So you have Stirling, pulse tube, and Gifford-McMahon. So they are use a regenerative cycle, like the way your PSAs or vacuum swing absorption works. A similar fashion it works. All this is called cryocoolers. These are the various ways of liquefying the gases to such low temperature. Now let us look at the major hazards of cryogenic liquid. First, it is extremely cold. The first hazard is it's extremely cold. You can get frostbite, if by mistake you touch a liquid nitrogen pipe, which has not been insulated, the moment you hold the pipe, there'll be some ice formation, but the moment you hold on the pipe, the skin will stick onto it. Okay, and it'll stick, and then you won't be able to take the hound, because immediately the moisture will condense, and the skin will peel out, or you will have a severe injury on your hand. And then is cold burn. It's the feeling of cold burn is similar to like putting your hand in fire. The only thing is, the difference is, in case of fire, the skins burn. Here it swells. It swells and it forms an yellowish pigmentation on the top. I'll show you some pictures later on. And hypothermia is, if you're working in such cold atmosphere, you may find breathlessness. You may, feel exhausted. You may start shivering. You start shivering, and you may fall unconscious and fall down. Okay. So it's hypothermia is similar to your experience in any cold, very cold, low temperature zone. If you happen to be in Himalayas on winter, or if you happen to go to the northern hemisphere in winter, in the night, when temperatures are below zero, so you may experience hypothermia, which is similar to what you experience here. Okay. Then there are flammability hazards, which is but specifically for hydrogen, methane, and LNG. Okay. The others are inert gases, and oxygen is an oxidizer. Okay. And there is another safety hazard, flammability hazard. I'll come back to it specifically for that. Okay. Which I will deal it separately. Enhanced combustion, the LOX, or liquid oxygen, which is called enhanced combustion. What happens is, oxygen as such, it's not doesn't have flammability. It's not combustible material. Okay. So the moment the problem with oxygen is, the moment you pour liquid oxygen onto a material, let's say you pour it on a Teflon. Okay, Teflon will catch fire. Or if you're wearing a clothing and you are exposed to an oxygen atmosphere, what happens is, the clothing will absorb oxygen and you come out of that zone. Okay, but the oxygen is still inside your clothing. So you happen to go outside the factory and you just light a cigarette, immediately your clothing will catch fire. That's the problem with oxygen. Okay, oxygen is not an it's not a flammable material, but the hazards come as soon as this. Okay, and even if you pour hydrogen on some material, okay, if you pour liquid hydrogen on a material, you can immediately catch fire if there's an ignition source. Okay, so oxygen is a very peculiar gas, and it has got its hazards, both flammability and oxygen enrichment and deficiency hazard, which I will take it up specifically during this webinar. And then we'll look into the oxygen deficiency hazard, which is specifically for when you're dealing with inert gas like nitrogen, argon, hydrogen, also even hydrogen. Okay, what happens is, when you're dealing with this liquid nitrogen or liquid argon or liquid carbon dioxide, what happens is, vapor displaces the oxygen by boiling off from the cryogenic liquids. Okay, so what happens is, this vapor, like liquid nitrogen vapor, will displace of oxygen. So you will end up in a situation where there's an oxygen deficiency in the room or in that particular area. So you will start experiencing shortness of breath, and then you will fall unconscious. You'll feel dizziness, and then you will, as the oxygen levels keeps dropping, you will go directly to coma and then to death. Okay, so this is very serious hazard, oxygen deficiency hazard, particularly in an enclosed or confined areas. Then there is another big issue with cryogenic liquid, is the high pressure formed during volume expansion of cryogenic liquid. What happens is, I told you, as you're seeing it in this chart, right? the volume expansion of each of these gases, as you see here, right? So what happens with this is there is a sudden expansion. Okay, so if there's a liquid and there is a heat source comes in it, or there is a vacuum has ruptured because it's stored in a flask. Okay, and suddenly the pressure will build up as soon as because it will expand in an uncontrollable fashion. So there will be a sudden build up of pressure, and then it will might explode, and the debris will also fly several kilometers, and it can cause several injuries. So those are specific hazards related to the volume ratio or expansion of cryogenic liquids when they vaporize. Okay, and there is another specific issue with liquid nitrogen is called the ionization radiation. What happens here is when you have the liquid nitrogen, what it does is it will try to because liquid nitrogen boiling point is lower than oxygen. Okay, so what happens is the liquid nitrogen will condense the oxygen. Okay, and it will form an oxygen rich environment, and which, if there is an ionization radiation in around that particular place, the oxygen will it will form O3, and then when O3 converts to, that is ozone converts to O2, it will give an explosion. Okay, this is very specific ionization radiation hazard peculiar to cryogenics. Okay, for certain applications. And then there is material embrittlement. Material embrittlement is certain materials like carbon steel, cast iron, rubber, and plastic. Okay, and they will be brittle. Okay, if you're using a plastic to if you're using a plastic what do you call plastic container to transfer liquid nitrogen, it will break. Okay, if you're using rubber as a gasket, or if you're using rubber as a in any of this cryogenic equipment, it's going to break. Similarly, cast iron, carbon steel, all these materials are result in embrittlement. Okay, then hydrogen embrittlement is very key specific, because hydrogen embrittlement, what happens is hydrogen is a very small molecule. Okay, so what happens is hydrogen will react with the material, and then it will react with oxidant in the material, form moisture, it start corrosion, and it will also puncture the material. Okay, hydrogen embrittlement is one of the serious issues. So hydrogen has to be stored in a very specific material where hydrogen embrittlement can be taken care. Okay, there's another issue with cryogenic is called thermal contraction. It means the material will shrink. Okay, there are many applications for it, but the hazard is that the materials will shrink, there's a contraction, and it will also change the properties of the material. It means the ultimate tensile strength and yield strength also will change at low temperature. So these are the issues with or these are the hazards, major hazards with cryogenic liquids. So we will look into each of this, and then how do we tackle it, okay, and later on in the webinar. What are the best practice when dealing with this cryogenic liquids? Because still I'm in the basic. Okay, so what are the best practice we can take care of it? Is use materials at cryogenic, only use materials at cryogenic temperatures. It means those materials like stainless steel, copper, or alloys, which can be used for low temperature applications. Only those materials has to be used. Okay, you can't use rubber, you can't use plastic, you can't use carbon steel, you can't use cast iron. Okay, so it has specific cryogenic low temperature material has to be used. That's the first thing. Next is always when you design, take into material property variation into consideration, because as I told you in the previous slide, the thermal contraction and enhance UTS and yield strength is one of the issues cryogenics. So always consider that in your material property variation with temperature. And then always consider you have to conduct or you have to evaluate an oxygen deficiency hazard analysis, which is prerequisite, okay, for any. It means you need to give you want to give a permit, or you want to give an authorization for a person to enter a zone. Then you need to carry out this oxygen deficiency hazard analysis, and based on that you need to give the permit. Okay, so it means he has undergone the training, or he has the PPE required for entering there, or he's aware of the hazards, and there is another person monitoring it. There is he has an individual oxygen monitor on his pocket, and there is an oxygen detector inside the room. All those things has to be taken care when you authorize him to enter that particular zone. Okay, and then we need to consider volume expansion and pressure rise. This is another best practice you need to take into consideration. As I told you, the moment cryogenic liquid comes exposed to heat, they will suddenly expand to almost 800 times. Okay, so there's a large volume, even though it appears to be very small in small container, but the gas will expand the size of the room or size of a building. Okay, so this
there are a couple of questions actually.
Yes, please.
Sanjeev Paruthi this side.
Yes.
One of the participant has asked, what is the JT cooler?
JT cooler is nothing but the Joule Thomson. Joule Thomson is the where you have, it's called constant enthalpy process. Okay, JT cooler is basically, you have you take a high pressure compressor. Okay, let's take you have air in, okay, at 1 bar 300 Kelvin, and then it's compressed to 200 bar at 300 Kelvin, and then goes to an heat exchanger, and then goes to the JT. JT is nothing but Joule Thomson valve. Okay, where it will suddenly expand. Okay, suddenly expand. So it is a constant enthalpy process. Okay, it's a irreversible process. Okay, it's a irreversible process. It's a constant enthalpy, irreversible process, and the temperature will drop, and then it forms liquid, and the vapor. This is the liquid form. When you have a Joule Thomson expansion, you will have liquid and vapor.
It's basically due to compression, pressure increase, so the temperature decreases, right?
See, this compressor is the pressure is increased, and then it comes to the expansion valve. Where is it? Just a minute. Comes to this expansion valve. Can you see my mouse rotation? Can you see that? Just wait. Let me think. Okay, I'll use this drawing till minute 10. Okay, now can you see this? Can you see this now on my PPT? Okay, now in Joule Thomson, what happens is this high pressure is suddenly dropped to very low pressure. Okay, so what happens is you'll form liquid here and vapor on the top. Okay, and the vapor moves back, and it's still cold, right? The temperature drops as well. So the vapor will go up and then cool the incoming gas. So this is a cyclic process which keeps happening till the sufficient amount of liquid is produced. Okay, and that's how the JT cooler works. Okay, JT coolers you will find it in any air separation plant also. Okay, but here this is all specifically for liquefiers. Okay, you want to liquefy any particular gas. You want to liquefy helium, for example. You want to liquefy hydrogen. You want to liquefy nitrogen, or you want to liquefy argon. You can use an JT cooler. Okay, is the question clear?
Yes, sir. You can just.
So I can proceed.
Yeah, sure.
Yeah, there is a.
It's clear, sir.
Yes, you can always stop me. I don't mind because I'll keep talking. So you stop me when you're.
Vishal, can we unmute people to make it more interactive? Is it possible, or sir has to cover first?
Yeah, we can just do
Let
that.
me.
Yeah,
No, wait. Like I will cover up the basic part, then you can unmute it. Okay, basic part will cover up most of the
Right, sir.
things. Okay.
yeah, sure.
So Vishal, over to you.
Yeah, sir, you can just proceed.
Yeah, I will proceed. Wait. But why is this pen? Wait. I have to move this. I think how it can go. Why is
Click on that pointer
PPT
again, sir, where you got that pin, no? Click on that pointer again.
uh,
Now it is fine. You can just.
yeah, it's not going. Okay, it's not moving to the next slide. That's the issue.
Just double click on the slides.
Okay. Okay. Now, fine. Now let's move on. I was here, right? So we then there is this volume expansion and pressure rise. Then there is you have to wear appropriate personal protective equipment, including eye protection, while handling cryogenic liquids. Now, for example, let me give you an idea. What happens is, suppose you have a cryogenic valve and you didn't wear the safety glass. You went near the valve, you don't know what it is, and you opened it, and that this liquid splashed on your eye. That's a very serious hazard, serious accident. Okay, what happens is the liquid nitrogen or liquid oxygen, whatever it is, it go and freeze your eyes. Okay, you have to what you want, you will not able to see, so somebody has to help you, or you need to go to the nearest shower or nearest wash basin. You have to simply keep the water flowing for 15 to 20 minutes, okay, near your eye. That's all. You just nothing will happen. You have to keep on allow the water to flow through the eye as long as possible. Otherwise because what happens in case of this cryogenic liquid is the tissue gets damaged. Okay, either in the hand, eye, or any skin part, the entire tissue gets damaged. Okay, it's as good as like it's a dead tissue. Okay, so immediately you have to wash with water, either your hand or your eye. Immediately you go and wash, and lukewarm water. No, it should not be hot water. You don't expose to the air also. You expose only to lukewarm water, and about 15 minutes you do it, and then you should be fine. Okay, I personally I have experienced all this, so I can tell you from my own experience. Okay, so that's the best way to do it. And then relief valve and vent valves should not be directed towards the people or material. That you should take care, because when we have the vent valve in the design, it is taking care. But if you happen to do some maintenance or some other, if you change the valve, the relief valve or vent line position, you should be not direct towards the people or another material. Because if it's direct to another material, what happens is this cold, when the vent out, it's a safety valve. If it vents out, then it will hit on that material, and if the material is brittle, then it will break. Okay, these are issues here. And avoid walking through visible vapor cloud. This is one of the issues. When we were young, we were not knowing it, so we used to walk in the vapor cloud. It looks like very nice, some Bollywood scene. But you should know, the moment you walk inside the vapor cloud, you are exposing in an oxygen deficient environment. Okay, especially with dealing with the nitrogen vapor or carbon dioxide vapor. So you are in an oxygen deficient environment. The longer you are inside the cloud, you will not realize, you will find little headache and then some dizziness, and you will fall down. And in few moments, if the oxygen concentration is very low, you will definitely fall down as immediately as possible. Okay, these are the very major hazards. We'll come to it later on. And you should always take into account flammability hazard associated with flammable gases like hydrogen and LNG. These are the best practices. Take into account unique hazard associated with oxygen. As I told you, oxygen has got two problems. One is deficiency, another is enrichment. Enrichment also issue, and deficiency also an issue. And then insulated cold surface so that air does not condense on them. So what happens in a cold surface is, suppose you have a material which is not insulated, okay, then what happens is this oxygen will condense. If it's a liquid nitrogen line, oxygen will condense, okay, and then it will create an oxygen enriched environment, so it becomes again a hazard. Okay, why it is hazard? Because if there's a grease or any contaminant or any combustible contaminant on the surface, chances of fire is very high. Okay, so there are several issues with that. Now, design for thermal contraction at cryogenic temperature. Now, always take into consideration thermal contraction at low temperature. Okay. Now, applications. Now, applications of cryogenics. See, here I'm not talking about application of industrial gases. Industrial gases, its applications are as good as infinity. So many applications catering to all kinds of industries. Okay, because those are all gas applications. Here I'm focusing on cryogenic applications, low temperature applications, which industrial gases also do. Okay, but we focus here on the low temperature application, which you'll find it in the national laboratories, research institutions, space organizations like ISRO. You will also find it in defense organizations or nuclear organizations, and medical, and including the veterinary hospitals. Okay, I'll come to it, including the horticulture. So air separation liquefaction, you have industry gas applications, which I don't want to cover it here, but there's so many, including the shrimp freezing, making your pizza ready, available at your store. All that is part of this application. And LOX and liquid hydrogen as a space exploration. For example, you take the stage 2 of an ISRO launch satellite, rocket. You have the liquid oxygen and liquid hydrogen as a fuel, and LNG as a transportation fuel. Okay, and use of liquid helium for cooling superconducting magnets. Okay, and for particle accelerator and fusion reactors, liquid heliums are used. Okay, and for also cooling infrared sensors. Okay, cryogenics used to preserve cells and other biological specimens. Sorry,
sir, one second.
Yes.
Is Mr. Atul Lokhande joined the webinar? Because his mail came to me. Vishal?
Yes, sir.
Mr. Atul Lokhande has joined the webinar.
1 minute, sir. Let me check.
Mr. Atul, if you are online, please confirm.
Yes, I can see him. He is online.
But just check the mail. Okay. Thank you. Please continue, sir.
Okay. Now, see, this cryogenic liquids are used to preserve cells. Okay, for example, if in case of veterinary industries, they use this for storing the semen. Okay, and it's also used for storing in biological field. They are used for storing your kidney, or storing your other cells or an organ. All these things can be stored in cryogenic temperatures, and cryogenic can be treated for materials to enhance their performance and machinability in the area of development. Like you can do for example, you want to do the simple shrink fitting. Shrink fitting is, you have a gear and you have a shaft, and you want to fit the shaft in the gear. Okay, so what you do is, you basically dip the shaft in liquid nitrogen, so the shaft will shrink, the diameter will shrink by a few mm. Then you insert it inside the gear, okay, with with the key there, and then allow it to slowly come back to room temperature, so it will perfectly fit there. Are you understanding? So that's all the applications. Also for machinability, means you want to have a better machinability of a particular material, you can also use liquid nitrogen for enhancing emissionability of that material. And in nuclear magnetic resonance and MRI, the liquid helium is used because the sensors are cooled to liquid helium because they're all superconductors. Okay, so for nuclear magnetic resonance and MRI, magnetic resonance imaging, the cryogenic liquids are used. Liquid nitrogen is also used for frozen food, like liquid carbon dioxide. Similar to liquid carbon dioxide, liquid nitrogen is also used for frozen food. Okay, where you have the shrimp freezing, or you take freezing of certain food items, and then can be exported. For example, many of the international fishing companies, they come to the Indian Ocean just outside the international border. Okay, and they come and do the fishing, and then they freeze it at liquid nitrogen. They have a liquid nitrogen inside the ship. They will freeze it, and then they export it to the various countries. Okay, similarly in India, like you have many shrimp cultivation farms where they cultivate shrimp, they freeze it to liquid nitrogen, and then they export it to the countries because it will be fresh. The advantage of freezing shrimp or prawns is it will be fresh like the way you get it at that time. Okay, so that is the kind of quality you'll get. That's why it is called, the liquid nitrogens are used for food freezing. Okay, wait. Now these are the applications. One is the collider, which is there in Geneva in Switzerland. Collider is uses liquid helium, okay, large quantity of liquid helium, because there is also superconducting magnets. Okay, so the proton will go at a high velocities, about 28 kilometers, I think. So it uses large quantity of helium. Then you have ITR cryo plant, that's in France, south of France. Okay, so this has all this liquid nitrogen, liquid helium. It's for fusion reactor. It's for energy production. It's a fusion reactor. It's collaboration with India also. Okay, this project is in collaboration with India also. Then you have for the space application. Okay, for the space application, let me use this. Okay, for the space application, this is called the turbo pump. The reason why turbo pumps are used is because you need to pump liquid hydrogen at very high pressure. Okay, at very high pressure for getting the impulse, because in a rocket you need the impulse, right? So that depends on the pressure. Okay, so to get that high pressure, you use the turbo pump. Okay, this is the turbo pump. And then you have a pulse tube cooler, large pulse tube cooler. Okay, this is again the one of the ways of producing. It's like a refrigerator. Okay, it's like a refrigerator for keeping the helium cool. Okay, this is again produced by Air Liquide. This is a collaboration with Air Liquide. This particular component is produced by Air Liquide. And then you have nuclear magnetic resonance, which I have already discussed with you, where you have the liquid helium superconductors. MRI, again you have liquid helium superconductors, these are the various applications of cryogenic liquids at very low temperature. There are several others, but I've just taken few photos when I put it here. Okay, now let us look at the now basic is complete. Okay, basic and application I've completed. Now if you want to open for questions, I'm ready for it. Okay, you can keep them unmuted so that
Yes, sir. So attendees, if you have any questions, please raise your hands. There is one icon there, raising the hand icon, so that I can just unmute you. Yeah.
Good morning, sir. I have a question.
yes.
So out of JT cooler and GM method, which is widely used?
Now, see, JT cooler is very popular one. You see, even if you take the air suppression plant, you have the JT cooler, right? If you take the air suppression plant, you have JT coolers. Okay, if you take any air suppression plants or you take any liquefier, you have the JT coolers. Okay. Now, in coming to the Gifford McMahon, it's basically regenerative cycle. Okay, GM coolers are
Okay, sir.
basically is a regenerative cycle where one set is taken online, other is under regeneration. Okay, it's like a cartridge where one is on one is put on live, other is on recharge. Okay, so the principles are one is this recuperative cycle, the other is called the regenerative cycle. Okay, so most of the industrial applications they use JT and Breton. Okay, these are the almost all air separation plants they use this, including for production of liquid hydrogen and liquid helium they use JT. Okay, if you look at this, I gave you two famous cycle called Claude cycle and Linde-Hampson cycle. Both are using JT. Only thing is in Claude cycle they're using expander. Okay, so there is no regenerative type of cooling done here. There is a heat exchanger. What happens here is you use a compressor at high pressure, send it to heat exchanger. Okay, 1, 2, and 3, and then in between you send it to expander, so you further drop the temperature, and then comes to the expansion valve here. Okay, I'll use this pen. Wait. Come to the expansion valve here. Okay, where what happens is this vapor at high pressure, very cold vapor at high pressure, it's still not liquid. Okay, so cold vapor at high pressure drops. Okay, it's an isoenthalpy process. Okay, it means enthalpy remains same, but
Yes, sir,
it's
got
a
that.
irreversible process. Okay, so what happens here is the vapor and liquid both will form at the exit. The liquid will accumulate here, the vapor will go back. It's a very cold vapor at low pressure, it is going back, and then it is cooling the incoming gas. Okay, and then goes to the goes to the expander, again further drops the temperature, and then further reduces temperature as the incoming gas comes. Okay, so that's how it's the whole process works. Okay,
So when we are dealing with at such high temperatures, while generation of this cryogenic liquids, so what are the materials that are being used?
see the materials you're talking about, the material of construction in this this heat exchanger or expander or this vessel, for example. Now they are all
Sir,
306 SS, 306 stainless steel.
okay, so
Okay, because that they are all applicable for low temperature application. 306 SS is perfectly fine for this such low temperatures applications.
and so for storage also it's the same 306 stainless steel.
Yes, or any of the alloys 306L, I think there is some there is one of this alloys they use for this containers also same. Okay.
My last question, sir. So is there any standard for storing cryogenics liquid?
Standards for storing now, if you the moment you want to store a cryogenic liquid in a tanker, it comes under pressure vessel. Okay, if the pressure is beyond a particular point, it comes under pressure vessel. So you use ASME section 8. Okay, okay, so as per ASME section 8 you will design the pressure vessel. So based on that you will but only thing you should take into consideration that material has to be for cryogenic application. The
Yes, sir.
thickness calculation will be based on ASME section 8. Okay,
Thank you, sir.
okay, that is how it is done. You can always stop me, there's no issue. Okay,
Hello, sir.
yes.
Yeah, I have a question. Like these liquids, they have any effect from the outside environment? Like when they are stored outside, like at the customer point when they are using. So seasonal wise, they do show any differences, like any effect.
Can you repeat the question? I'm not getting in what context you're talking.
these liquids, when they are using at their end, at the end user,
Yes.
outside environment, like seasons will be changing, like summer, winter, raining.
It won't matter at all because temperature is pretty low, no? Here, see, for example, if you take this, let me show you this graph. The temperature here are, this, for example, liquid helium, it's almost like 4 Kelvin. Okay.
Okay.
It's almost like, 269, minus 269 degrees centigrade. Okay. It, only thing is the difference it will make for it, delta T, which you talk about for vaporizing or for any heat exchange. The delta T will be slightly increased. So for example, in winter in a very cold country, for example, this thing you're handling in Alaska, the temperature outside may be around say minus 30. Okay, so delta T or in India if you're handling it will be plus 30. So delta T will increase by 60 degrees. That's all.
So according to that, we need to ensure the parameters related to this.
See, actually, if you ask me, see, high temperature, what is happening is certain losses you might increase a little bit. Okay, if if your vacuums are not proper, but that is all taken care when you bring it. But the issues with temperature are something else. Because in air separation plant, if the air temperatures are high, then your production will be less because the lower the temperature the of air, lower the temperature, denser the air is. Okay, so then you will have if your temperature is high, the density is less. So when you are handling in air compressor, then in a cold temperature it's more efficient. Okay. But in case of warm temperature, it may not be efficient. Those are some of the issues. But for example, if you are using, like for example, this man, here he's pouring some liquid nitrogen from a flask or something. Okay, if you're doing it in a cold country, depends on the moisture level. Okay, it depends on the moisture level, depends on the temperature. For example, you will see the same thing in Alaska as well as in Nagpur, same thing, because vapor will form. Okay. So temperature in Nagpur may be 40 degrees, in Alaska may be minus 40, but vapor will form because it is boiling off. It doesn't, only difference will be plus minus 40 degrees or 50 degrees, that's all. Okay.
Okay, that will not make any hazardous environment surrounding.
No.
That much difference it will not come.
Same, it will be same.
Okay, okay, sir.
Only thing is to take care that it doesn't happen in a closed room. Okay, that's all.
Okay, okay, okay.
Let me remove this. Okay. Now, where we you can always stop me. Don't know issues. Now we stopped here, right? Okay. Now coming to concentration, mixture, and explosion. Okay. Now again, I told you that cryogenic liquid classified broadly as inert gas, flammable gas, or oxidizer. So nitrogen is basically inert gas, oxygen is an oxidizer, argon is inert gas, hydrogen is a flammable gas, carbon dioxide is non-combustible, and helium is inert gas. Okay, so the flammable is only the hydrogen when you're talking about, and LNG. LNG also comes under flammable. Okay. Now, one of the important thing to be considered when you're looking at the any particular gas is the material safety data sheet, MSDS. You have to go to MSDS for the material you're handling. Okay. So there, in any MSDS, you will find first is called the CAS number, CAS. Okay. So based on this number, they are if you see a liquid nitrogen tanker, or if you see any storage tank, you have to look at the symbols like this. You will find a symbol like this. Let me draw using a pen. You will see a symbol like this. Okay. you will see a symbol like this. Now what is the symbol indicates is this 3, it's an health hazard. This one is health, and this is the flammability indicator, and this is the instability indicator. Okay, now instability, most of these cryogenic liquids is never an issue. They are not unstable. Okay, so it will be always 0 for most of it, except for acetylene. Acetylene is, even though the industrial gases deals with acetylene, I will not consider that in cryogenics, because you know, they are not coming to low temperature applications. Okay, but they are unstable. And acetylene, if you take acetylene gas, they are highly unstable. Okay, health wise, if you look at it, nitrogen gas, it's a problem. Okay, flammability is 0. Okay, this is called NFPA rating. Okay, this is coming from the fire department. Okay, so fire department will see all these industrial gases. You take the nitrogen, oxygen, hydrogen, anything, it comes under hazardous material. Okay, if you're transporting any of these gases, okay, you may argue that, you know, nitrogen is not flammable, but still comes under hazardous gases. Okay, so any form of any transportation of these gases comes under hazardous. So there is something called an orange board in the front and the back. Okay, so it's called the class 2 under transport of dangerous goods. Okay, now nitrogen is basically colorless, odorless, inert, is non-flammable. Okay, but containers may explode when heated or may rocket. Suppose, you know, you heat a diwar, or you heat a liquid nitrogen container. Okay, then the vapor will vaporize very fast, and then it will explode. Same with gas cylinders. So first there is a safety aspect of it, but the moment you suddenly increase, the safety may not work so much, because the reason is the rise in pressure is so high that the whole thing will explode. Okay. The health hazard with nitrogen is frostbite. Okay, it will cause serious and permanent injury, and then asphyxia. That means oxygen deficiency in the atmosphere will cause dizziness, unconsciousness, and death. Okay, so these are the issues with nitrogen. Now let me come to the next. Oxygen. Wait. Oxygen is colorless, odorless, non-combustible, will not burn. Okay, it is non-combustible, but it's a strong oxidizer. As a liquid, it has a pale blue color. Okay, now if you look at the symbol here for gas, it shows 000, and there is 1 in the white. White is the special factor. It's mentioning that it's an oxidizer. OX means oxidizer. You will also have a symbol like this. Okay, so it means it can catch fire, and the cylinder is pressurized. Okay, so this too you'll also find in all this when you're handling oxygen cylinders. And in case of liquid oxygen, you'll find 3 here. In case of gas, you don't find. Gas is there's never an issue. Okay, but in case of liquid, yes, there is a health hazard. It means it can cause frostbite, asphyxiation, cough, and then it can it has other oxidizing properties. Okay, so this is one of the major hazards with oxygen. It means you will, if you are exposed to a very oxygen rich environment, is also hazardous. Okay, because never feel that, you know, if the place is rich in oxygen, it's not harmful. It could be harmful. Okay, so basically what happens, if the oxygen levels are very high, you will have a coughing coming, because your body cannot take so much oxygen in. Okay, first you'll start coughing, and then, you know, you'll find a little bit breathlessness. Okay, because oxygen levels are pretty high. And there are other hazards with it, because oxygen will absorb in your clothes, and then if you're exposed to any fire hazard, you can catch fire. Okay, so these are the issues here. Argon is it's colorless, odorless, inert. There's another issue with argon, is it's heavier than air. Okay, so that need to be considered. Okay, that's why it's called, there is a special mention here called SA, and it's non-combustible gas. Okay, content may explode when heated or may rocket. And liquid argon, you have the health issue, same like nitrogen and oxygen. Only thing is here you will have a same as the nitrogen, liquid nitrogen, same. Now hydrogen gaseous form, the hazard is only flammable. It's not health, it's nothing to do with instability, no other special precaution. Okay, so you will always find this symbol here, danger. Okay, and in case of liquid hydrogen, it is hydrogen is basically colorless, odorless, extremely flammable gas, and the lower flammability limit and upper flammability is 4% to 75%. Okay, and then it's an invisible flame, you cannot see it. Okay, I'll show you some videos. And then contains gas under pressure, may explode if heated. And liquid hydrogen causes serious or permanent injury, frostbite. Vapor inhalation causes breathlessness, dizziness, unconsciousness, even death. Okay, so in case of liquid hydrogen, you will see 3: health as well as flammable 340. This in any tanker, liquid hydrogen tanker, you will find this symbol. Okay, now wait, now I'll show you that video so it will be more clear.
Sir, actually there is no audio.
You're not able to hear the audio?
No.
Wait. You're not able to hear the audio. How do we?
I think it's fine. Let's not. We may not be
Yes?
able to play the audio. That's fine.
Wait, let me check. Now we can hear.
No, sir, still it is the same. Okay, sir, you can just explain these parts. That's it. Just showing the video.
Wait. Then, but I'm a little surprised why it's not playing. Wait. Let me try from here. Give a second, please. See, these are available on YouTube. You can always have a look at it anytime. Yes, this one. I'll play from here. Let's see how it works. Are you able to hear now?
No, sir, it is still the same. Maybe I think we cannot play video because it is connected to the mic. Mic is the priority. Audio from the mic is the priority.
Yeah, so the voice transmission will not take place with that.
Right.
So if I mute the mic, then can you hear that?
I don't think so, sir.
I don't
Yesterday?
think, sir, it will take. No, sir, the transmission will not happen, I think.
Just wait, let us try now.
That's just water vapor condensing
Yeah, it is
in
fine.
surrounding air.
Can you hear?
Once
Yeah.
hydrogen gas has reached normal air temperature,
Can you hear now?
completely invisible.
Yes, sir, it is audible.
Because it's so light, gas released in any
Audible?
enclosed space
Yeah, it is audible.
collects it. For
Okay.
this reason, hydrogen monitoring devices should be placed as high as possible. Hydrogen can be converted to a liquid if it's pressurized and subjected to extremely cold temperatures, which is how it's normally stored and transported. It's much more economical to transport and store hydrogen as a liquid because the liquid expands into a gas at a ratio of 850 to 1. That means you need 850 tankers of hydrogen gas to deliver the same amount of material as one tanker of liquid hydrogen. Liquefied hydrogen is one of the coldest materials used in any industrial setting. It's normally at 423 degrees below zero Fahrenheit. The only colder liquefied gas is helium. If you work with liquefied hydrogen, be sure to follow the precautions to avoid low temperature burns. We'll talk more about that later. Hydrogen is often used as a fuel. When the space shuttle took off, it burned a combination of liquid hydrogen and liquid oxygen to create the necessary thrust. Hydrogen is also the most environmentally friendly fuel on Earth. When it burns, the only byproduct is water. Hydrogen's other main application is in creating controlled atmospheres, which are needed for certain industrial processes, like heat treating, steel manufacturing, and finishing for special types of metal. Hydrogen is highly flammable, but it's not as dangerous as most people think. A hydrogen flame is extremely hot, but it doesn't radiate much heat into the surrounding area. By comparison, fires from gasoline and natural gas radiate far more heat, and they have the potential to last much longer and do a lot more damage. When hydrogen burns, the flame is almost invisible. It burns clear, creating just a faint blue cast. Might actually hear the sound of a hydrogen fire before you see anything. If for any reason you suspect a hydrogen fire, contact Libby immediately. To work safely with hydrogen, it's important to remember that it takes hardly any energy to ignite it. A spark of static electricity from combing your hair is about 1,000 times more the amount of energy needed. The key to working safely with hydrogen is eliminating any possible sources of ignition. Liquefied hydrogen is always stored inside vacuum-jacketed tanks. These tanks are like big thermos bottles, essentially a tank within a tank. With hydrogen, the inside tank is always stainless steel because other metals become brittle at such a low temperature. The storage tank and all other components connected to a hydrogen handling system must be bonded and grounded according to accepted industry practices. Bonding consists of connecting all the components together to avoid any difference in electrical potential from one component to another. Grounding means that the system must have a good electrical path directly into the earth to dissipate any electric charge. In hydrogen systems, bonding and grounding are essential to prevent any sparks that might start a fire. In the event of a leak or other emergency, an emergency stop button is available that will shut off the supply of hydrogen from the tank. The area around the storage tank should be kept clear of material, cars, and other vehicles. Backing in a gas delivery truck takes a lot of room, so be sure to maintain a wide, clear path from the road to the storage tank. The The tank on a gas delivery truck is basically the same as a stationary tank, double-jacketed, holding liquefied hydrogen under low pressure. Only trained industrial gases delivery persons certified in hydrogen handling systems should handle unloading. Also, the truck must be grounded to the local bulk handling system before unloading to help prevent sparks. Employees who work around hydrogen should always be aware of any unusual conditions that they see at the tank, such as excessive icing, discharge of liquid or excessive vapor from the tank, tank piping, or a safety relief valve. These are not normal conditions, and they indicate a problem. If any of these conditions are observed, call the Lindy emergency phone number posted at the tank. The piping should be located in protected areas where workers cannot damage it when they're using forklifts, trucks, or other equipment. If a change is planned to the tank or piping design, or if additional capacity is needed, have an engineer look at the system. Hydrogen systems are designed precisely for the material and the sizing of the components. Contact Lindy if any changes are planned to the tank or tank piping systems. Workers face two main risks from hydrogen: extreme cold and fire. The personal protective equipment that they wear must address both. Workers should wear a long-sleeve shirt and pants of FRC, fire retardant clothing. Synthetic fabrics are not acceptable because of their tendency to create sparks from static electricity. Workers must also wear eye and face protection, conductive or static dissipative safety-toed boots, and loose-fitting insulated gloves. It's very important that liquefied hydrogen never be trapped in a container or a section of pipe anywhere in the bulk handling system. Safety relief devices must be installed wherever the pressure can build up to dangerous levels. Here's why. Imagine boiling water in a pot with the lid clamped on. What would happen? Water boils. Steam pressure builds up. And before long, you've got a very hazardous situation. If liquefied hydrogen is trapped in a container or a pipe with no venting, you've got the same situation. Even though it's very cold, liquefied hydrogen is actually boiling as it evaporates. This can build up tremendous pressure, enough to cause piping to rupture. Safety relief devices must be installed in all piping and storage systems, between all block valves, and anywhere else that liquefied hydrogen may become trapped. Also, all electrical equipment within 25 feet of a hydrogen handling system must be explosion-proof. Safety relief valves on a hydrogen system take advantage of the gas's lightness. They direct the gas into a vent stack, which discharges well above the ground. When hydrogen is vented, it just goes straight up the stack. Unlike some gases, hydrogen is not a problem for the environment. Hydrogen bulk handling systems also need low-temperature shutdown devices. These prevent hydrogen that's too cold from entering any pipes or other equipment that are not acceptable for operation at very low temperatures. Sometimes liquid hydrogen systems must be purged to clear them for maintenance and inspection. Helium is the only gas that can be used for this process because it's the only one that won't freeze solid at the temperature of liquid hydrogen. For purging systems that carry hydrogen gas, nitrogen may be used, but product purity concerns may dictate that helium be used for this operation as well. All affected employees should be trained on the material safety data sheet for hydrogen. Material safety data sheets are available from Lindy, and they provide important safety information, including the hazards of the product, first aid and accidental release measures, personal protective equipment, as well as proper procedures for handling and storage. As we said earlier, liquefied hydrogen is one of the coldest materials on Earth. At 423 degrees below zero Fahrenheit, this presents a tremendous risk of low temperature burns. In this respect, it's even more dangerous than liquefied nitrogen or CO2. Workers should never touch liquid hydrogen pipes, valves, or other equipment with their bare hands. Even if their hands are dry, they'll stick instantly because the super low temperature of liquid hydrogen will draw moisture right out of their skin. Even if workers are wearing gloves, contact should be avoided with these components. Also, there's a danger from the vapor produced by liquid hydrogen. It can damage delicate eye tissue. Workers should always wear eye protection if they may be exposed to cold vapor. If liquid hydrogen comes into direct contact with the skin, it will produce instant frostbite. Contact of even a few seconds will be very painful.
I think the people are saying that the voice is not audible for the video.
Not audible.
So I think stop it.
Wait.
Low temperature burns should never be rubbed or warmed.
Okay. I think see.
You can just little bit give the summary. Maybe sir, you can give the summary of the video.
Hello. Can you hear me?
Yes, sir, your voice is audible.
Yeah, okay. Now, fine. What I suggest is, see, for the audience, for the participants, is you can always go back to, you just go to YouTube, subscribe for Linde, and there are a whole lot of safety videos which I'm playing. Just played to you just now. I don't know what's the audio issue, but you can always go back to this website and you can always have a look at it. Okay. So I showed you the link where you can have a look at it. Now, coming back to quickly, let us cover up this so that we can go to the question answer sessions. Okay. Now, hydrogen, I think the video covered most of it, but the main problem here is flammability limit, because it's 4% to 75%. Okay, and it is invisible flame. Okay, so there is in that video that it will show you what is that invisible flame. I don't know, unfortunately, that we couldn't cover it, but you can always go back to that YouTube site and check it out. Okay, and then there are other low temperature frostbite issues like other liquid nitrogen. And carbon dioxide is there is a same health hazard both in terms of gas as well as liquid, but there is one more issue here, is it is slightly toxic. Okay, it is slightly toxic. So that is one of the hazards here. And many of this carbon dioxide are used in the for making clouds and all the stuff in drama and dance as well as in movies. Okay, so that this has to be taken into consideration, like because it's heavier than air, that's why you find the clouds on the ground and you feel that you are in the top of a cloud or something. But there is an hazard here, because prolonged exposure can lead to dizziness without warning. Okay, and then frostbites. Now, helium is as a gas, there is no issue, no flammability, no health issue, no instability issue, but the only problem is asphyxia. Okay, because it doesn't support, it will displace oxygen, and so you will find breathlessness. And in case of liquid helium, the problem is frostbite, and it's very low temperature. It's almost close to 0 Kelvin, almost 4 Kelvin, right? So it's a serious issue here. Now coming to the main hazards related to all these gases, one is oxygen deficiency. Okay, now let me cover up as early as possible because we are running short of time. Okay, one is the volume of oxygen. So you see the moment it is below 19.5. Okay, this you should always remember. See, normally in air you have 21% oxygen, right? So the moment it drops below 19.5, okay, the moment it drops below this point, then it is hazardous. Okay, so that you always keep that in mind. And so as the oxygen level drops, your vision will reduce, then further it drops, the dizziness, then impaired attention, judgment, 12%. It will be, you will be completely you lose the muscular coordination, loss of consciousness. Then you immediately move, nausea, vomiting. 6, you will almost go to death, okay, a coma. So these are the issues with oxygen deficiency. That's the symbol, you will see it in outside any oxygen deficiency room or oxygen deficiency hazards. Okay, then let's move on. Oxygen enrichment, you'll see the symbol, okay, where the oxygen gas leaks in a confined space can result in an oxygen enriched atmosphere. Okay, so leak can come from various sources such as compressed oxygen cylinder, liquid oxygen dewar, oxygen pipeline. And then enrichment can also occur in uninsulated cryogenic surfaces also. As I told you, if you take a liquid nitrogen pipeline, if the what the liquid nitrogen pipeline does is it will try to condense the oxygen in here, okay, moisture and then oxygen in here. So you'll find a confined oxygen enriched environment on the surface of the pipe. Okay, this is one issue. And then major hazards of oxygen enrichment are fire and health. So high oxygen enrichment increases the risk of fire, material burns faster, and clothes absorb oxygen. Now if you take a, you take your the gloves which you use for cryogenic application for handling cryogenic liquid. Okay, now the gloves, what you do is you pour liquid oxygen in on the gloves, okay, and you light that using a matchstick. It will catch fire. That's a hazard with liquid oxygen. Okay, and then there is a health hazards like oxygen toxicity. It means high oxygen content is called oxygen toxicity. It's called hyperoxia, where oxygen is more than 50%. Okay, so this can also result in health hazards. Now flammability limit, all of you know that there is 3 things required. A triangle, the fire triangle. You need oxygen, an oxidizer. Okay, either it can be oxygen or nitrogen peroxide, any oxidizer. Okay, fuel can be anything. It it could be your petroleum source or hydrogen or anything. And heat. When these 3 things are there, the fire will catch. So there is something called low flame limit and upper flame limit. For ethylene, it is 2.7 to 36%. Propane is 2.4 to 9.5. Hydrogen is 4 to 75. The problem with hydrogen is the range. Can you see here, 4 to 75? So that is the issue with hydrogen. At various range, it catch fire. Now coming to the safe storage and handling procedures. We'll look into the properties, hazards, cryogenic tanks, and then we'll look at the various type of cylinders and dewars in laboratory. What are the precaution, first aid, emergency, and personal protective equipment. Okay. Now the properties. You can always stop me if I'm going fast, or if you feel that you're not following. All of you are hearing this? Hello?
Yes, sir, it is audible. You can just go ahead.
It is audible. Yeah. So again, I come back to properties of hydrogen, nitrogen, argon, and oxygen in comparison with LNG and nitrous oxide and carbon dioxide. See, your boiling points are given here, and then you have the flammability range for hydrogen it is 4 to 75%. For LNG it is 4 to 15%. Okay, 4 to 15% is for LNG, and for other gas you can also see the density as well as the gas quantity vaporized for 1 liter liquid. Okay, so this needs to be considered whenever you have this. If you see here, 1 liter for helium it is 748, for hydrogen is 844, and for nitrogen 691, argon 835, and for oxygen 853. Because this is another issue, as I told you, with cryogenic liquid, they'll expand a small quantity of liquid will expand into large volume of gas. Okay, and they vaporize. Okay, so cryogenic liquid are all commonly called cryogenic. Okay, now this I'll move to the weight. Now they are classified. Cryogenic liquid hazards are basically they are cold. This is a symbol you will find. Okay, whenever you deal with cryogenic liquids, you'll find it is in DIVAR or cryogenic cylinders. You'll find this symbol, and this symbol is also you'll find it in the DIVAR, or not in DIVAR. You'll find it in the cryogenic cylinder because pressure build up and rupture. Okay, you will also find this symbol in any confined space, okay, where oxygen deficiency is possible, okay, or oxygen cylinders are stored. Okay, so there you'll find this symbol. You'll also find this symbol if there is an oxygen enriched environment or possibility of oxygen enrichment. Okay, now this is these are the standard symbols for safety. Okay, one is the frostbite. The first one is a frostbite. The other one is for the materials like most plastics and ferrite steels. I think some noise is coming. Some noise. I'm not sure here. Okay. This one is for the cold nature of the cryogenic liquefied gas. Okay. And this is the ratio. I just told you that 1 liter of liquid gas can produce approximately 600 to 850 liters of gas. And then there should be no smoking. Okay, no visible ignition source, and no entry. Okay, so this symbols has to be placed whenever you're dealing with cryogenic liquids. Wait. Now, if you're having a cryogenic storage tank at customer station, it looks like this. You have a storage tank and a vaporizer, and then you have all this safety relief valve and all this. Okay, so so this is for every tank you will have a pressure relief and rupture disc. This is a standard, and all the pressure vessels will be designed as per ASME pressure vessel code. Okay, and cryogenic liquid cylinders and DIVARs. This is called the cryogenic liquid cylinders. What is the difference between a DIVAR? This is the DIVAR. DIVAR, it is nothing but a flask. Okay, it is like a flask for storing liquid nitrogen. But here the difference is here it is at atmospheric pressure. It means there is one cap there, and then as the liquid vaporizes, it will just slowly escape from this cap. Okay, and there is no pressure built up in this DIVAR. But in case of a cryogenic liquid cylinder, there is a pressure build up apparatus inside. Okay, so you can if you want vapor form, you can get it. If you want a liquid form, you can get it. You want it higher pressure, or you want to transmit liquid from one container to another container, this is possible using this cryogenic liquid cylinders. Now these are the handling instructions for when you're dealing with cryogenic liquid cylinders. You'll find that It's an oxidizer if you're dealing with oxygen, and it is a non-flammable gas, okay, because that's a symbol here. And it has to be always in the vertical position, and you're dealing with cryogenic liquid, okay. So the handling instructions are given. You'll find this in every container. What are the dangers and warning signs? What are the first aid and other informations, okay. So what are the precautions you need to take into consideration, and what are the first aid? Okay, precautions are like you need to wear the PPE for low temperature skin and eye protection. Do not mix different cryogenic liquids or change the container. And to avoid oxygen deficiency or enrichment, permit required. Okay, to avoid flammable or explosive atmosphere, permit required. No smoking, open flame or any area with oxygen, hydrogen, LNG. Only materials suitable for cryogenic temperature must be used. Do not dispose cryogenic liquid via drains or a closed system. Remove moisture. These are the precautions need to be taken. If you have the first aid unit is if you have this problem with lack of oxygen, then you take him to a ventilated place, a fresh air. Okay. The other is frostbite is you just wash it in lukewarm water, and do not the stick clothes will also stick. Okay, so do not remove the clothes, you just wash it, that's all, and then it automatically it will come out. The moment you try to pull out your sleeve or you try to pull out the cloth where it is stuck to your skin, then it will spill out your skin also. Okay, that is to be taken into consideration. Emergency is if you are having there is a for example oxygen, if you have any combustible materials when there is a spill, okay, so this could be an hazard. Also you should have an exit plan, okay, and all these sites should have water spray. You should also have you should not touch or walk to spill products. Leak, if there's a leak, you should stop the valve where it is leaking, and you should avoid the cryogenic liquid or gas entering the waterways, sewer, basement, or other confined areas. Allow spilled cryogenic liquids to evaporate. Okay. Isolate area until cryogenic gas or liquid has dispersed. These are the emergency consideration you should do. And PPE you should wear is the hand protection. Then you have your reinforced toe cap shoes, safety glasses, face shield, helmet, hard helmets, and then safety helmet. Then you should, if you are working in lab, you should have the lab coat and apron. The reason why you have to wear this clothes is because you pull to avoid any spillage on your clothes. Okay. Compressed gas transportation. Now coming to compressed gas transportation, this is again this is coming from the classification. As I told you, it's an hazardous goods. So it under UN classification, it comes under class 2. Okay, flammable 2.1, and the inert gases and oxidizing 2.2. Okay, so you'll find this is a simple flammable gas, non-flammable gas, and oxidizer. So transport category is 2 for flammable gas, and transport category 3 for non-flammable gas and oxidizer. So you'll find this, for example, your tanker, you will see there, you will find this is a liquid nitrogen tanker. You will see 1977. It means the UN number is 1977. Okay, and the hazard category is 2, transport category 2, it's non-flammable. So this you'll find it in all the tankers. This is how you'll see. Okay, with the phone numbers and all that, and where all it will be placed. The orange board will be placed the front and the back. Okay, and cryogenic container. These are the MSDS safety data sheets. Okay, this is how it looks. And what are the liquid transportation we need to consider? Okay, I'll speed up this. These are available. Okay. So major hazard of cryogenic liquid I have already covered in the basic. Okay, so I will skip this side. Now coming to the hazard risk analysis, all of you are there? I'm not able to hear anybody.
Sir, everyone is here.
Okay, now I will unmute all the participants because this is one case study we'll take. Now we are almost come to the last part, but this is a very, very important part. Okay. So in the case study here, you know, in March 81, you can read it. Okay. So there was a technician. Now let me give you in very short form. There were 3 technicians working in Kennedy Space Center. So they entered a compartment in the Space Shuttle Columbia program, and which has been purged with gaseous nitrogen. So there was there were communications were not clear, or the procedures were not clearly defined. The technicians were not aware that there was a oxygen deficiency problem here. Okay, so they went inside this chamber, and the first 2 went inside the chamber, collapsed. The third one entered to just check what these 2 were doing. The third one also collapsed. Okay, so this example illustrates common features of oxygen deficiency hazards, accidents, a lack of awareness that hazard exists. Because the problem is, you know, this nitrogen is you will be clueless. For that matter, any inert gas, you will be absolutely clueless. What is happening, you won't know. Okay. So this is one of the issues. So how do we tackle this? This is the case study we have taken here. Okay, so wait, minimize this. Okay, now basics of oxygen deficiency hazard is you should be aware of oxygen deficiency hazard, but never use cryogenic liquid regardless of the amount without considering whether or not oxygen deficiency may result. Okay, so there will be oxygen whenever you're using a cryogenic liquid, especially the inert liquid nitrogen or liquid argon or liquid hydrogen or liquid helium, you will always have this oxygen deficiency hazard. Okay, so so you need to have a written procedure on ODH risk post by this particular setup, and then level of analysis required very depending on the situation. Okay, so there you can go in for detail. You know, you can do a simple calculation of for finding out ODH risk, or you can even do a modeling. Okay, I'll show you all the different methods to finding out, do the risk analysis for ODH. Okay, now as I told you in the previous thing is regarding oxygen division 19.5%, that you always keep in mind that anything below 19.5 is unsafe. Okay, so and it depends on your how much detail you want to go, okay, for and doing the analysis. So there are some mitigation measures to be taken for the risk of ODH accident, emergency plan, and you should always train the staff, visitors, contractors on the nature of hazard, safety requirement, and emergency response. Okay. So the mitigation measures for ODHs: do not conduct cryogenic activities in confined space. First point, period. Okay. So don't conduct any cryogenic activity in confined space. Suppose, for example, if you take a liquid oxygen cylinder, liquid nitrogen cylinder, okay, inside a room or inside a laboratory which is closed, then you have a ODH risk. Clear. Point, period, finished. Okay, so it means the person you cannot, and person cannot enter that place, maybe a laboratory or maybe a research room or whatever it is. Okay, do not transfer cryogen in closed vehicle with people. If you're carrying a liquid nitrogen tanker, is a cylinder inside a closed vehicle, if you have people inside that, then no. Okay, so you can't use liquid nitrogen or liquid helium underground. There's also issue. So example, in Europe, you know, if you want to transport liquid nitrogen tanker inside a tunnel, not allowed. You understand? He has to take a different route. For example, from Grenoble, he wants to go to Turin. It's only few kilometers. This side is France, that side is Italy. He has to take a D route away from the tunnel. Okay, so he can't cross the Mont Blanc tunnel at all. Okay, the reason is that the entry point will be blocked because of certain problems are there with, because it's in he's carrying liquid nitrogen. If there is a accident inside the tunnel, okay, then it will create serious problem for the people who are commuting through this tunnel. Okay, because it will be an oxygen deficient environment inside the tunnel. I don't know in Pune, Mumbai belt, it is still allowed or not with liquid nitrogen tankers through the tunnel. Okay, but this is one of the issues when you're handling with liquid nitrogen. Vent relay valve outside the building in open space. Employ lintel. Lintel is kind of an opening in the, if any room you have, confined room, you have a, out on the top of it you have an ventilation window, right? So that is called lintel. That should be always there, open, for release of any inert gas for it to escape. Okay, reduce inventory of cryogenic fluids or compressed gas. Training on ODH and notify people on ODH hazards. And then you should have an oxygen monitoring and alarm, audio and visual both. Okay, it means there has to be a sonar, it means someone has, it has to sound, as well as visually it will show the danger, something like that. Okay. Personal oxygen monitor, 2% rule and third person observer. It means 2% will go inside a space where they have to work, and the third person has to observe from outside what these two people are doing. If these two people are in danger, the third person has to act, not go inside it, but he has to start an emergency button where, you know, the ventilations are switched on, or things, actions are taken so that, you know, these people can be saved. Okay, so he has to sound the emergency. Now ventilation and other active system, emergency escape packs. Okay, now let us take a simple problem. You have a laboratory. Okay, you have a small lab. The size of the room is 2.5 into 2.5 into 3 meters, which has got 160 liters DIVAR of liquid nitrogen. Okay, so liquid nitrogen has any ODH risk in this? Yes, because the volume of the room is 1875 meter cube. Volume of liquid nitrogen vaporized from 160 liters is 115,200 liters at 300 Kelvin at 1 atmosphere pressure. So volume of nitrogen vaporized is much bigger than the size of the lab. So oxygen will be displaced and there will be a ODH trace present in the lab. Okay, are you getting it? Any questions here?
Not yet, sir. You can just go ahead. At the end of the session, we can just answer a few questions.
Yeah. Okay. So this is the fatality factor versus percentage of oxygen. You see, the moment you below 19.5, so let's say when you start 18, fatality rate is still 0. It means 18% you may find little uneasiness, but still you won't, nothing will happen to you. Fatality rate means you won't die if the oxygen rate content is less than 80%. Okay, the moment the problem happens is when it's 80% to 8%. Okay, so the fatality rate is slowly increasing. Okay, and the moment it crosses less than 8%, it's almost, you are like, you know, you'll fall down unconscious and then you'll go to coma. Okay, there's a possibility, even if you are here, if someone recovers you at this point, then they can take you to emergency and, you know, bring back you to life. But beyond this, very little doubt. You may be in coma, but you know, you may not come back. Okay, so this is the fatality rates, and you'll always find this symbol here. It's based on the oxygen deficiency hazard, ODH. 1, 2, 3, 4. 1 means you know, you need to have the training done to enter. 2 means you know, it is, see, can you see here, there's an 10 to the minus 5 to the minus 3 per hour. So this is means, you know, you should have a training, and then you should have also have an oxygen monitor. 3 means you should have the more than one people to enter the site, and then you should have a personal oxygen monitor, and then you should have oxygen emergency hazard training. All this thing has to be done here. 4 means you should have a personal oxygen sensor in your pocket, as well as oxygen sensor in the local room, and then you should have gone through training, you should have gone through the emergency procedures, and then there's another person who is looking at you know, 2-person rule and third person observer. That has to be also followed. Okay, because in ODH4, hazard classification for ODH fatality rate is greater than 10 to the minus per hour. Okay, so chances of fatalities are very high in ODH4. So these are the various ODH classifications. Okay, and warning signs should be there for all. Oxygen monitor should be there for all. Ventilation only for ODH4. Okay, the moment the oxygen level is dropping, the ventilation will be on. Okay, relief valve and piping arrangement, okay, as per the requirement. Routine, the training for all. Oxygen monitor is only for ODH2, 3 and 4. Multi-person, that is 2-person rule, is ODH2, 3 and 4. Unexpert observer, that is the 3rd-person rule, is only for ODS 3 and 4. And self-contained breathing apparatus only for ODH4 and ODH 9 is the medical approved, CBA qualified. Okay, and ODH hazards are only for the for visitors are ODH 1 and 2. Okay, so this is how it is classified, and this is how the risk assessments are done. Okay, you can also do the modeling. For example, you know, this is a tunnel. Okay, and you can use any ANSYS or CFD tools, you know, and find out like where you can find high concentration of oxygen, where the concentrations are low. Okay, so from this you'll know that the area where the person is entering, concentrations are low. It means you know, he has to, there has to be ventilation system here, or you know, this has to be. Okay, now coming to the last part is the plotting the impact of cryogenic liquids. See, cryogenic liquid and present in the future is, you know, quantum computing. The liquid helium is going to play a very important role in quantum computing. Okay, that is one of the futures. All this is future of cryogenics. Then you have this ITR Tokmak fusion energy reactor in France, with collaboration with 5 different countries: Japan, India, European Union, and South Korea. Okay, so they are building a fusion reactor using liquid helium. Okay, so this is another promising area as far as energy is concerned. Then you have this squid. Squid is basically a superconductor. Okay, and it's basically high temperature superconductors, which runs on a chip. Okay, and you can also use it for you can also use liquid helium for HTS conductors, and where, you know, you reduce the transmission losses in case of a cable assembly. Okay, and then last is cryonic. Cryonics is storing organs. Even human body can be also stored at very low temperature. Okay, so there is no bounds for cryogenics when it comes to applications. So with this, I leave now the floor open for questions. You ask more questions, better the session will be.